Okay, so that takes care of using the ideal gas law and the combined gas law, and now we're going to do some stoichiometry dealing with gases. We had stoichiometry back in the last chapter, and it's sort of back in a way. And we're going to deal with it in terms of molar volume. We're also going to take a look at Dalton's law of partial pressure, a little bit about mole fraction, and then some examples of using those. Okay, so next, let's look at the concept of molar volume. All right, so we have something called STP, and STP stands for, S stands for standard, T represents temperature, and P represents pressure. Okay, so there we are. Temperature, standard temperature is 0 degrees Celsius or 273 Kelvin. Standard pressure is 1.00 atmospheres. So temperature, standard temperature is not 25 degrees Celsius. It's 0 degrees Celsius or 273 Kelvin. All right, so there we are. And what does STP give us? The volume of 1 mole of any gas at STP is equal to 22.4 liters. That's what STP gives us. So the volume of 1 mole of any gas, it doesn't matter how big the gas is, it doesn't matter how small the gas is, any gas at STP is equal to 22.4 liters. Okay, so let's just sort of look at an example of what this means. So at 0 degrees Celsius and 1 atmosphere, STP, 1 mole of the gas H2 occupies 22.4 liters. 1 mole of the gas argon occupies 22.4 liters. Now, note, this is H2, the molecule H2, so it actually has 2 hydrogen atoms in the molecule. Here, we just have the element argon with the with 1 atom of argon in the molecule. And, you know, even if you have a very large molecule, a relatively large molecule like methane, CH4, that still also only occupies 22.4 liters. In fact, if you're doing a reaction and your reaction comes out to give you some very large molecule, let's say 1 mole of something that's normally not a gas, let's say water. If you have a mole of the molecule water as a gas, it will occupy 22.4 liters. So what's nice about setting things up at STP and knowing the volume of any gas at STP is it allows you to do stoichiometry involving gases. Okay, so let's look at a very simple example. This is not so much a stoichiometric problem, but just a simple little problem where you convert from volume to where you convert from mass to volume. So here's my example. So the question asks, how many liters will 17.5 grams of the element neon occupy at STP, where STP temperature is 0 degrees Celsius and pressure is equal to 1 atmosphere. Okay, so that's the question. How many liters will 17.5 grams of neon occupy at STP? Alright, so let's look at this word problem. That's what you always want to do. When you have a word problem, you read the word problem. Okay, so I've got 17.5 grams of neon. And I would like to know how many liters I occupy with that many grams of neon. Okay, now it doesn't look immediately like we can do a whole lot with that. It doesn't even look like it's connected. How many liters are you going to get out of that many grams? What? What does that mean? I also should note that this is actually neon gas. Alright, now we're going to go ahead and write out the STP statement. So I said 1 mole of any gas, including neon, would have 22.4 liters. So let's go ahead and write out what we know about that. So we're going to say 1 mole of neon gas will occupy 22.4 liters. Okay, that I got out of the thing being at STP. I'll probably give you the number 22.4 somewhere on the exam once again, but you do have to recognize what to do with that number. And so the value is, at STP, you have 22.4 liters of any gas, and neon is a gas. So we're going to go ahead and say that. That still doesn't relate my grams to my volume, because I only got now moles and liters. It doesn't tell you anything about grams, and I got grams here. So what can we do to go from grams to, let's say, moles? And you remember, you think to yourself, the definition of the mole. What's the definition of the mole? The definition of the mole says 1 mole of any element is equal to the atomic mass of that element, or the molar mass of whatever. Okay, so let's look at the periodic table. So here's my periodic table. I look up the element neon. Here's my neon. I'm going to just rewrite that in a big thing right over here on the periodic table and on my little word problem sheet. So I got neon, and my little block of the periodic table says this. So that's my little block of the periodic table. Alright, so neon has on the bottom the big number 20.1797, and we got 10 on the bottom. This is our molar mass, right? So then we can say that 1 mole, and I'm abbreviating mole as MOL, of neon gas is equal to 20. And I'm just going to, this has 3 significant figures. I'm just going to round it up to 3 significant figures. So I'm going to say 20.2 grams of neon. So there's another thing that I can use to solve my word problem. Alright, so we've got this, and we have that. And I have grams of neon, and I would like to have liters of neon. So it looks like what we're going to do is we're going to start out with the amount that we have. We're going to use these 2 conversion factors. We're going to just do plain old dimensional analysis, and we're going to end up with liters of the gas neon. Sounds good, right? Alright, so let's go ahead and do that. So what we're going to do is we're going to start out with the amount of stuff that we have. Whenever you're given a word problem that involves some sort of conversion, you always start out with the amount that you have. And the amount that we have is 17.5 grams. This doesn't tell, it says how many liters. That doesn't tell you anything. STP just tells you the temperature and pressure. That doesn't tell you anything. But we're starting out with this much of the stuff. So we have 17.5 grams of neon. And then we're going to use these 2 conversion factors to go from grams to volume. We're trying to go from grams of neon to liters of neon. So that's the overall thing that we're trying to do. We're trying to go from grams of neon to liters of neon. So here's our grams of neon, and we're looking at these 2 potential conversion factors. Sometimes you'll start with the problem and you say, oh, I'm missing something, and then you'll come up with the other conversion factor that you need. So here's my grams of neon. I got grams of neon converting to moles of neon. So that looks like a good candidate for the next thing that we want to write down for my conversion factor. Do I want grams on the bottom or do I want it on the top? And it looks like you would want it on the bottom because I'd like to cancel it out. So I'm going to say 20.2 grams of neon. And I'm going to write on top 1 mole of neon gas. So I look at this and I can see that my grams of neon will cancel my grams of neon, and I have moles of neon as my final answer at this point. If I stopped here, I'd just end up with moles of neon. I'm going to go ahead and use my second conversion factor. So this right here took care of our first conversion factor. There's my first conversion factor. I use that one up. So now I'm going to use my other conversion factor. My other conversion factor is going to go from moles to liters. So I want moles on the bottom, so I would like to cancel out my moles. So I got 1 mole of neon on the bottom, and I've got 22.4 liters of neon on top. I can see that I will be able to cancel out my moles of neon on the bottom from my moles of neon on the top. And the only unit that I have left is liters. And I was looking for liters of neon. So I can see that if I go ahead and crunch the numbers through, that my answer will give me liters of neon. So I'm going to go ahead and crunch that number through, and I will get 19.4 liters of neon for my final answer. I have 3 significant figures here, 3 significant figures here, 3 significant figures here. 1 is not 1 significant figure because that's a definition, so that has an infinite number of significant figures. So that is the correct number of significant figures, so there we are. 19.4 liters of neon for my final answer. Okay, so there we are. I think what I'll do next is, instead of going over Dalton's law of partial pressure, I'll go ahead and do my stoichiometric problem for gases next. Okay, so there we are.